Hello there, and welcome to Mysteries of Earth. The shocking discovery. The screen is dark. A single point of light appears. A distant star. Slowly, ghostly data overlays ripple across the image, hinting at a hidden world. Narrator. Calm, measured, but with a tremor of awe. For centuries, we have looked at the night sky and wondered, are we alone? Are those stars cold, lifeless embers? Or are they suns, warming other Earths? For most of human history, the answer has been a silence so deep it seemed eternal. But that silence is breaking. A glimmering animation of the James Webb Space Telescope unfolds in space like a golden origami. Its honeycomb mirrors catch starlight and scatter it into rainbows of data. 200 years ago, telescopes could only hint at the shapes of planets in our own solar system. 100 years ago, the idea of detecting life across light years belonged to science fiction. And yet, 120 light years away, in a small, dim star system catalogued as K218, Webb has found something no one expected to see so soon. The faint, unmistakable fingerprints of life itself, a whisper across the stars. We zoom into a spectrograph, delicate peaks and valleys that look like a heartbeat. The discovery didn't arrive with fireworks. It arrived as a pattern, a series of dips and rises in starlight, so subtle that only the most sensitive instrument humanity has ever built could hear it. Webb separated a planet's faint glow from the glare of its parent star, then split that glow into its component colors, a cosmic barcode. And hidden in that barcode was a signal no geologist or chemist could explain away. The narrator's voice drops to a near whisper: dimethyl sulfide, methane, hydrogen interacting in disequilibrium. 3 chemical clues, like footprints in alien sand. Each alone could be a curiosity. Together, they form a signature that on Earth is proto-C, it only by life. We cut to Earth scenes: marshes bubbling methane, microscopic plankton releasing dimethyl sulfide into the air, cows grazing under a setting sun. Here at home, dimethyl sulfide is produced almost exclusively by living cells. Phytoplankton drifting in our oceans, invisible architects of Earth's atmosphere. Methane, too, is woven into the metabolism of countless organisms. It breaks apart quickly under ultraviolet light, vanishing unless something replenishes it. On a planet bathed in starlight, a persistent supply of methane is not a stable chemical backdrop. It's an alarm bell. Something is exhaling. The 99.7%. Numbers swirl on screen. 68%, 95%, 99.7%. Astronomers live by probabilities. Extraordinary claims demand extraordinary evidence, and the threshold for extraordinary is high. Webb's data reached that threshold, a 99.7% statistical confidence that the signals we are seeing are not noise, not instrumentation error, not a trick of starlight. In everyday language, that's as solid as science gets, without being absolute. In cosmic terms, it's the difference between a rumor and a revelation. We pan over the telescope drifting against the Milky Way. The implications are staggering. For the first time, we are not speculating about life out there. We are measuring it, seeing its chemistry transform an entire world's atmosphere across 120 light-years of emptiness. A planet named K218b. Visual: a blue-green world wrapped in gauzy clouds, orbiting a small red sun. K208b, a bland name for a world that may upend everything. It orbits within the habitable zone of a cool dwarf star, where liquid water could exist. Its atmosphere is rich in hydrogen, yet its temperature hovers near 120 degrees Fahrenheit. A curious balance between warmth and stability. On Earth, deep-sea vents with similar heat nurture organisms that thrive without soothes in light. If such niches exist there, life could have begun not once, but many times, diversifying into forms we can barely imagine. The narrator poses a question like a challenge. What would it mean if on this hydrogen-rich world, methane isn't a waste gas, but a breath? What if life there metabolizes in ways our textbooks don't yet describe? We cut back to the spectrograph. Lines of light bend into new patterns. From speculation to detection, until now, the search for life beyond Earth was a story of potential. Maybe here, perhaps there, someday, when our instruments are stronger. Webb changed that. It wasn't designed as a life detection mission. It was meant to study the first galaxies. But its infrared eyes turned out to be sensitive enough to read the atmospheres of small, temperate planets. That is the quiet miracle behind this discovery. We built a window into the early universe and ended up glimpsing our cosmic neighbors. Images flash, engineers assembling mirror segments, scientists staring at code. A control room at 3 a.m. The first researchers to see the data reportedly sat in stunned silence. Generations of exoplanet hunters had dreamed of this moment. A biosignature, clear enough to publish, defend, and withstand scrutiny. And yet, here it was, quietly waiting in a string of numbers, a planetary breath. When we speak of biosignatures, we often imagine alien forests or glowing oceans. But life leaves subtler marks. It pushes a planet's atmosphere away from chemical equilibrium, just as Earth's oxygen would vanish without photosynthesis continually replenishing it. K208b's atmosphere is a living equation. Its gases are not random. They are interacting in ways that hint at cycles. Intake, transformation, release. It may not only be habitable, it may be busy. The narrator's voice slows, each word deliberate. This is not just life surviving. This is life shaping a world. Shifting the human perspective. Cut to archival footage. The first photographs of Earth from space, pale blue, marble. Then the Hubble Deep Field. Every great leap in astronomy changes more than our data. It changes us. Copernicus moved Earth from the center of the universe. Galileo's telescope revealed moons orbiting Jupiter. The discovery of galaxies beyond our own expanded the cosmos 1,000,000-fold. Now Webb has taken the next step, showing that the universe is not just filled with worlds, but with worlds already alive. How will we teach our children about the night sky after this? Not as a cold void, but as an ocean of potential biology. Not, is there life? But what kind? How many? And how close? The dawn of a new era. The music swells, hopeful, but eerie. And this is only the beginning. Webb's data on K208b is the first domino. Over the next decade, it will survey hundreds of star systems within 100 light-years, searching for atmospheric fingerprints. Advanced algorithms will comb through the spectra, looking for combinations of molecules beyond oxygen or methane. Agnostic biosignatures that could reveal life we don't yet know how to name. We stand at the threshold of a new age, in which, are we alone? Becomes a measurable question, not a philosophical one. The narrator breathes out, almost a sigh. The silence between stars is no longer empty. It is filled with the faint collective breath of living worlds. A breath across the stars. Opening shot. A black ocean of space. Pinpricks of starlight shimmer like scattered embers. One faint red star glows at the center. Over it drifts the spectral trace of a planet's atmosphere, a living barcode across the darkness. Narrator. Measured, low, slightly hushed. In Chapter 1, we stepped onto the stage of a single alien world, K2 18b, and saw the first hard evidence that life might not be confined to Earth. But a single planet is only a whisper. To understand what Webb has really shown us, we must follow that whisper back to its source. Across 120 light-years of empty space, something is breathing. The language of light. We see a ripple of starlight breaking into rainbows, a spectrograph stretching across the screen. Light carries stories. Every atom, every molecule leaves a signature when it absorbs or emits. For a century, we have used this language to read the chemistry of stars. Only in the last few years have we learned to apply it to the thin veils surrounding distant planets. Webb's golden mirrors are tuned to the infrared, where cool molecules whisper instead of shout. That is why it can see what no instrument before it could: the faint chemical tracings of life. The narrator leans in. Dimethyl sulfide, methane. Carbon dioxide in disequilibrium with hydrogen. On Earth, these are not just chemicals. They are breaths, exhalations of metabolism, invisible graffiti left behind by living cells. Cut to Earth. Phytoplankton swarming beneath sunlit waves, wetlands bubbling, ice-bound microbes metabolizing in darkness. Dimethyl sulfide, DMS, is one of the most potent. In our own oceans, tiny drifting plankton release it as part of their life cycle, shaping clouds and even influencing climate. Outside biology, DMS is almost impossible to sustain. Methane, too, breaks down swiftly under a star's ultraviolet glare unless something replenishes it. Together, these gases are like footprints in fresh snow, transient, unmistakable, and telling us who has passed by. A hydrogen-wrapped world. The screen fills with an artist's impression of K2 18b, a world swathed in gauzy clouds, pale sunlight filtering through a hydrogen-rich sky. What makes K2 18b so strange is its envelope of hydrogen. On Earth, hydrogen escapes quickly. Our gravity cannot hold it. But this planet, larger than our own, yet far lighter than a gas giant, seems to be wrapped in a thin hydrogen cloak. This chemistry alone would be unusual. Yet within that cloak, Webb saw the traces of DMS and methane. The combination is startling. Hydrogen is reactive. It should strip away or transform delicate organics. And yet here, these molecules persist. Something is creating them faster than they can be destroyed. Something active. We zoom in to swirling clouds and hypothetical alien microbes drifting like snowflakes. Could it be a deep, warm ocean, rich with hydrogen, where exotic cells metabolize methane instead of oxygen? Could it be a biosphere, unlike anything in our textbooks, using chemistries that make our own seem parochial? The narrator pauses, letting the question echo. Beyond coincidence, numbers scroll across the screen. Rates of photochemical breakdown, estimated production, observed abundance. When scientists first analyzed Webb's data, they tried to explain the signal away. Could volcanoes release dimethyl sulfide? Could strange geologies produce methane in such abundance? Could some unknown process mimic biology? Each scenario fell apart under the weight of the numbers. The concentrations were too high, too steady, too coherent. Statistically, the evidence reached the sacred threshold, 99.7%. Not absolute proof, but a confidence strong enough to change the conversation from maybe to very likely. On cosmic psyches, Kalis, it is the difference between a rumor and a revelation, a planetary factory. We drift through a simulation of chemical reactions in the atmosphere, methane and hydrogen combining to form amino acids. Laboratory experiments on Earth have shown that under the right conditions, methane and hydrogen can combine into complex organics, even amino acids, the building blocks of proteins. K2-18b's atmosphere may be acting as a vast chemical workshop, producing precursors to life, even as life itself exerts its influence. The result could be a feedback loop. Biology seeding chemistry, chemistry feeding biology. Imagine a sky where clouds are not just water droplets, but habitats, where life floats between layers, metabolizing methane the way we breathe oxygen, where the atmosphere itself is a living system, not just an envelope of gas. Echoes of Earth, shadows of the unknown, cut back to Earth. Deep-sea hydrothermal vents glowing in the dark, tube worms clustered around superheated water. The closest analogs we know are not on the surface, but in the abyss. In hydrothermal vents where sunlight never reaches, life flourishes on chemical energy alone. Temperatures near 120 degrees Fahrenheit, like those estimated for K2-18b, turn out to be ideal for building complex molecules without destroying them. Could this be the cosmic sweet spot? Just as stars have preferred masses that let them burn steadily for billions of years, perhaps planets have preferred temperatures where biology thrives, mutates, and diversifies. The narrator's voice becomes reflective. If so, then K2-18b is not a freakish outlier, but an example of a universal rule. Where conditions converge, life emerges. A new kind of atmosphere. Graphics show layers of gases swirling around the planet, each labeled with a different energy source. Webb's data hint at more than one metabolism. Different organisms may be using different gases, creating a layered ecosystem from some surface to stratosphere. One layer could be rich in methane breathers, another in hydrogen recyclers, still another in microbes producing dimethyl sulfide as a byproduct. An atmosphere not just mixed, but stratified by life. A planet breathing with many lungs. If true, K2-18b may already be more diverse, more active, than Earth was at a comparable age. Evolution under a warm, stable sky could proceed faster, generating biospheres of unprecedented complexity. Listening for seasons. We see time-lapse graphics of a planet's atmosphere changing over months. Webb is only beginning to watch. On Earth, our atmosphere changes with the seasons as life blooms and recedes. The next step is to see if K2-18b's gases fluctuate over time. Do methane levels rise and fall? Does dimethyl sulfide peak like plankton blooms in spring? If so, we won't just be seeing life. We'll be watching its rhythms. The narrator leans forward. Imagine measuring the heartbeat of a planet across 120 light-years. That is what is about to happen. The meaning of a breath. Cut to archival footage. The first heartbeats of a newborn recorded on an ultrasound. Every breath tells a story. For the first time, we are hearing the breath of another world. Not metaphorically, chemically. K2-18b's gases are a message written in the universal language of atoms. I am alive. And if one world can speak this way, how many others are whispering, waiting for us to listen? The 120° F, sweet spot, opening shot. A slow zoom into a glowing droplet suspended in darkness. Inside the droplet, complex shapes form and dissolve. Chains of molecules assembling and breaking apart like living constellations. Narrator. Calm, reflective. Life is a dance between energy and fragility. Too little energy, and chemistry crawls. Too much, and molecules shatter before they can combine. Somewhere in between lies a narrow, fertile band where order arises from chaos. In the search for alien life, astronomers have a name for that balance: the Goldilocks zone. Not too hot, not too cold. But Webb's latest findings hint at a second, more intimate Goldilocks. Not a place in space, but a temperature in time. The quiet furnace, cut to a montage. Steaming vents on Earth's ocean floor. Geothermal pools simmering in Yellowstone. Lab beakers filled with amino acids. On Earth, some of the most promising scenarios for life's origin take place not in icy comets or scorching volcanoes, but in warm, mineral-rich waters between 110 and 130 degrees Fahrenheit, roughly 45 to 55 degrees Celsius. At these temperatures, amino acids link more readily, membranes form spontaneously, and catalysts accelerate reactions without burning them apart. It's a quiet furnace, warm enough to spark complexity, gentle enough to let it persist. K2-18b's estimated conditions, around 120 degrees Fahrenheit beneath its hydrogen sky, fall exactly into this range. Coincidence or a cosmic hint? The chemistry of possibility, we see animations of amino acids snapping together into chains. At room temperature, most chemical reactions that build life's building blocks proceed sluggishly. They need a push. At 120 degrees, molecules move faster, collide more often, and climb the first rungs of complexity with surprising ease. Lipids, the precursors of cell membranes, self-assemble into bubbles. Nuke, leotides form longer strands. Catalytic cycles emerge. Push the thermostat higher, and these same molecules unravel. RNA breaks down. Proteins denature. Lower the temperature, and reactions stall, frozen in potential. The sweet spot is narrow, but powerful. A cradle of acceleration, where the improbable becomes routine. Narrator leans in. Could it be that this temperature band is not unique to Earth, but a universal incubator, written into physics and chemistry themselves? Evolution's fast lane. Archival footage. Time-lapse of bacteria dividing, colonies spreading across a petri dish. Temperature doesn't just affect the birth of life, it governs its speed. In biology, every 10 degrees Fahrenheit roughly doubles or triples metabolic rates, up to the point of destruction. At 120 degrees, metabolisms run briskly, mutation rates rise, and natural selection has more material to work with. Evolution accelerates. On a young world bathed in mild warmth, complexity may emerge in centuries instead of millennia, ecosystems in millennia instead of eons. Life could leap forward faster than our planet ever allowed, reaching stages of sophistication we can scarcely imagine, while our own world was still microbial. The narrator pauses, letting the image sink in. What would a billion years of Earth-style evolution look like, compressed into 100 million? The hidden history of warmth. Visual. Artists' rendering of early Earth under a dim sun, steaming oceans, meteorites falling. Earth itself may have passed through such a phase. The young oceans, heated from within by radioactive decay, and above, by a faint sun cloaked in greenhouse gases, could have hovered near this same temperature. Perhaps our own earliest cells arose not in a tepid pond, but in a warm, globally favorable cradle. If so, we are the children of the 120-degree furnace. This possibility reframes the search for life. Instead of looking only at distance from a star, the classical habitable zone, we must also consider interior heat, atmospheric composition, and how they combine to create a planet's internal thermostat. Warm worlds in a cold universe. Cut to a map of exoplanetary systems, with dots colored by estimated surface temperatures. Webb's catalog already hints at dozens of planets, where surface or subsurface temperatures converge near this band. Some orbit dim red dwarfs. Others hide oceans beneath ice crusts, but are heated by tidal forces. Hydrogen envelopes, thick atmospheres, or subsurface seas can all stabilize a world's warmth, even when starlight alone would not suffice. In other words, the 120-degree sweet spot may be common, not rare. Warm worlds hidden in cold systems, habitats wrapped in gas instead of ice. Narrator. If chemistry sets the stage and temperature provides the rhythm, perhaps life plays the same melody everywhere the conditions are right. The Goldilocks within Goldilocks animation, a nested diagram showing the traditional habitable zone around a star, and inside it, a narrower band, labeled optimal biochemistry. We once thought habitability was a single shell around a star. Now we see it may be fractal. A Goldilocks within a Goldilocks. Distance gives you liquid water. Temperature gives you thriving chemistry. Both must align for life to bloom. This insight may explain why some planets in the right orbit are barren, while others, farther away, seem alive. Without the internal warmth or atmospheric insulation to hit the sweet spot, they are cold laboratories with no experiment running. With it, they may be cauldrons of diversity. Beyond earthly blueprints. Visual. Imagined alien microbes shaped like ribbons, disks, and crystalline webs. Of course, not all life will mirror ours. At 120 degrees is under hydrogen skies, metabolisms may not use oxygen at all. Proteins may fold differently. Cell membranes may incorporate exotic lipids. Yet the principle remains. Chemical reactions accelerate with warmth, and self-organization emerges more readily. It is not that life requires our recipe. It is that life, whatever its recipe, likes a warm kitchen. Narrator's voice softens. This universality is humbling. We are not special because our oceans were perfect. We are special because the cosmos provides many kitchens, and one of them cooked us, reading the thermostat of distant worlds. Visual. Webb's spectrograph, comparing different atmospheric temperatures. How do we know a planet's internal temperature from light years away? Indirectly, through models of its atmosphere, gravity, and star. Hydrogen envelopes act like blankets, trapping heat. Methane ratios change with temperature. Even cloud heights tell a story. Piece by piece, astronomers reconstruct the invisible thermostat. K2-18b's readings fall neatly into the band. Other candidates are lining up behind it. The sample size is small now, but growing. Within a decade, Webb and its successors could measure dozens of atmospheres with enough precision to chart the cosmic temperature curve of life. A universe awakening montage. Multiple planets turning slowly, their atmospheres glowing, a faint heartbeat of light superimposed. If we find that many of them cluster near this same range, it will be more than a coincidence. It will be a signature of a universal process. Chemistry's bias toward a certain warmth, evolution's fondness for a certain pace. the universe will look less like a random scatter of worlds and more like a nursery with familiar cradles. That realization would change not just science, but philosophy. It would mean life is not an outlier, but an expected outcome whenever the thermostat is set. Just so. Life without sunlight. Opening image. Total darkness. A camera glides through a black ocean. Slowly, faint blue glows appear. Shimmering columns rising from the sea floor like underwater chimneys. Strange creatures pulse with ghostly light, their bodies swaying in invisible currents. Narrator. Hushed, resonant. When we picture life, we picture sunlight, green leaves, warm oceans, a blue sky overhead. But here, 2 miles beneath our own seas, the sun is a myth. No ray of daylight penetrates this abyss, and yet it is teeming with living things. What we're seeing is not just an oddity of Earth. It may be a preview, a mirror held up to countless worlds where sunlight never rises. The dark hearth along the mid-ocean ridges of our planet. Seawater seeps down into the crust, meets magma, and erupts back upward as superheated plumes. These are hydrothermal vents, black smokers and white smokers, spewing mineral-rich water at hundreds of degrees. The surrounding sea is near freezing. At the interface, gradients of heat and chemistry create something extraordinary: energy without light. Here, bacteria do what plants do on land, but without photosynthesis. They use chemosynthesis, tapping chemical reactions to build organic molecules. They turn hydrogen sulfide, methane, and metals into living tissue. Around them gather entire communities: giant tube worms with no mouths, clams the size of footballs, eyeless shrimp with backs that glow like embers. They are nourished not by sunlight, but by the invisible wealth of the Earth's interior. Narrator. This is life's second engine. It shows that biology is not chained to the sky. It can root itself in the planet's own chemistry, making food from stone and heat. And if it can happen here, why not elsewhere? Alien oceans beneath ice. Visual. Cut to an illustration of Europa and Enceladus, their icy crusts cracked, plumes spraying into space. In our own solar system, we already suspect entire oceans hidden beneath ice. Europa, Enceladus, Titan. Worlds where sunlight is weak or non-existent, but where tidal flexing keeps water liquid and warm below the surface. In 2017, Cassini flew through the plumes of Enceladus and found hydrogen, methane, and complex organics. A recipe not unlike our hydrothermal vents. Picture a moon covered by miles of ice. Beneath, a dark sea warmed from below. Minerals seeping from the crust, energy gradients as sharp as any on Earth. No sun, no sky, but chemistry enough to fuel entire biospheres. Narrator leans in. Could such places host not just microbes, but ecosystems? The alien equivalents of our vent communities, evolving in darkness for billions of years. The power of chemosynthesis. We see a lab experiment where simulated vent conditions produce amino acids and membranes. In the lab, scientists have recreated vent-like environments. They find that iron-sulfur minerals can catalyze the formation of amino acids and even primitive cell membranes. Electrical gradients across thin mineral walls can drive energy cycles similar to those in living cells. In other words, hydrothermal settings do not just sustain life, they may help it begin. On an exoplanet wrapped in hydrogen, under an ocean of water or ammonia, vents could produce both the spark and the fuel. Chemosynthesis may be the universal fallback, the way life takes hold when light is scarce. Narrator. We once thought photosynthesis was the pinnacle of energy capture. Now it looks like an adaptation, layered on top of something older, a deep, planet-driven metabolism that might be far more common in the universe. Strange bodies for strange worlds. Visual. Speculative alien organisms drifting near a vent. Translucent ribbons, metallic shells, colonies shaped like snowflakes. If life arises without light, what forms might it take? Without vision, eyes become irrelevant. Without sunlight, pigment loses meaning. Instead, organisms might evolve sensory systems based on pressure, magnetism, or chemistry. They might glow not to attract mates, but to communicate in the dark. They might store energy like batteries, charging from vent chemistry and discharging slowly as they drift. Even on Earth's vents, we see hints of this. Microbes with metal-based enzymes, worms hosting whole gardens of symbiotic bacteria inside their bodies. The further we look, the stranger it becomes, and all of it driven by a single principle: harvest energy wherever it is, however it comes. Narrator, reflective. These are not the alien monsters of science fiction. They are reminders that our own planet is already alien, and that biology is more inventive than we imagine. The slow clock of darkness. Archival footage, time-lapse of vent communities over months. Life in the dark moves differently. Growth can be slower. Lifespans can be longer. Mutations accumulate at odd rhythms. Evolution might produce creatures of great age and patience, cultures, if any ever arose, that measure time not by days, but by cycles of heat and chemistry. On a planet where the sun never shines, what would intelligence look like? Would it invent technology at all? Would it send signals we could recognize? Or would it remain hidden, thriving in silence, invisible to telescopes that search only for light? Lessons from our own abyss. Visual. Scientists in submersibles descending into vents. Every dive into Earth's deep ocean expands our sense of possibility. In 1977, before the first vent discovery, few biologists would have predicted entire ecosystems without sunlight. Today, we know such ecosystems cover vast areas of the seafloor, and that's just our small planet. Multiply that by the billions of worlds with oceans under ice, and the implication is staggering. The galaxy may be riddled with dark biospheres, each humming quietly out of sight. Narrator's voice softens. The irony is that our search for life has been biased toward stars, toward light. But perhaps most life is not in the starlight at all. Perhaps it is down below, in hidden oceans and buried aquifers, thriving beyond our view. A new target for Webb and beyond, visual. Webb's mirror with overlaid graphics of subsurface oceans. Even telescopes like Webb, designed for starlight and atmospheres, are beginning to hint at subsurface worlds. Variations in plumes, gravitational tugs, and spectral signatures can betray the presence of hidden seas. Future missions may sample them directly, flying through geysers or drilling through ice. When that happens, the test will not be sunlight but chemistry, ratios of hydrogen to methane, isotopic fingerprints, complex molecules where they should not be. The same clues that pointed to life on K2-18b may reveal life where no star ever shines. The philosophy of the dark, cut to black. A single point of bioluminescence pulses like a heartbeat. Darkness is not emptiness. It is potential. For most of Earth's history, life lived without light, microscopic, patient, persistent. We are the latecomers, the creatures of a rare blue window in a mostly dark cosmos. Realizing this changes how we think of life. It is not fragile. It does not require a sky. It is a planetary process, seeded in warmth and chemistry, flowering wherever conditions allow. Our sunlight civilization may be the exception, not the rule. The methane mystery. Opening image. A soft, ghostly glow, drifting over a distant planet. Lines of data trace across the screen like a heartbeat. At the center, one simple molecule appears, over and over again. CH4. Methane. Narrator. Steady, curious. In the previous chapter, we saw how life can thrive without light, feeding on the chemistry of the deep. Now we face a single clue. A fingerprint so small it fits on a cocktail napkin, but so powerful it shakes our ideas about alien worlds. Methane. Colorless, simple, 1 carbon and 4 hydrogens. It shouldn't be there. And yet on K2-18b, it is everywhere. The Vanishing Act. Cut to a graphic of methane molecules rising in an atmosphere and being broken apart by ultraviolet light. Methane is a fugitive. Under a star's radiation, it breaks apart within decades. Ultraviolet light shreds it into fragments. Hydrogen escapes. Carbon recombines. Without a constant source, methane should vanish. On Earth, this is exactly what happens. Volcanoes emit a trickle of methane, but our air stays methane poor because sunlight destroys it faster than geology can supply it. Yet in K2-18b's atmosphere, Webb detects methane in quantities that defy the models. Enough to imply not a trickle, but a torrent of replenishment. Where is it coming from? The geological hypothesis. Visual. Cross-section of a planet's mantle venting gases upward. The first guess is always geology. Could deep reservoirs release methane through volcanism? Could chemical reactions in a hydrogen-rich crust produce it abiotically, as serpentinization does on Earth? The team modeled these processes. Each one fell short. Without extreme conditions or impossible rates, they couldn't sustain the observed abundance. In other words, nature's usual non-biological sources can't explain what Webb sees. Something else must be feeding the sky. Narrator. Softer. This is Weiss. Read the story shifts from chemistry to life. Methane as a signature of breath. Cut to a montage of Earth's wetlands, cows, termites, and microbial mats. On Earth, methane is overwhelmingly biological. Microbes in swamps, guts, and ocean sediments exhale it as a byproduct of metabolism. Even ancient methane trapped in ice often bears isotopic fingerprints of biology. When astrobiologists draw up lists of biosignatures, methane paired with certain gases always ranks near the top. But methane alone is ambiguous. It's the company it keeps that matters. On K2-18b, Webb finds methane alongside dimethyl sulfide and carbon dioxide in a hydrogen-wrapped atmosphere at the right temperature for complex chemistry. That combination, abundance plus context, is what makes scientists lean forward. Disequilibrium. The cosmic tell visual. 2 graphs overlaid. Expected versus observed gas ratios. A planet in chemical equilibrium is like a still pond. Left alone, reactions settle into predictable ratios. Life, by contrast, is a force of disequilibrium. It pushes gases out of balance because it is constantly making, breaking, and recycling molecules. K2-18b's atmosphere is out of balance. Methane persists despite conditions that should destroy it. Carbon dioxide levels are lower than expected. Hydrogen ratios hint at ongoing processes. It's as though we're looking at a living metabolism on a planetary scale. Narrator. Could we be seeing the exhalations of alien microbes drifting in its sky? Or perhaps something stranger, organisms that metabolize in ways we haven't imagined, but still leave the same telltale signature of disequilibrium. A planetary methanogenesis. Visual. Speculative alien cells in a warm ocean, producing methane bubbles that rise to the surface. Imagine a global ocean beneath a hydrogen sky. At its warm interface, microorganisms harvest chemical energy from minerals and excrete methane. Billions of tiny bubbles rise, venting into the atmosphere. Winds carry them around the planet. Ultraviolet light breaks some apart, but more always comes, keeping the concentration high. To an observer light years away, it would look exactly like what Webb is seeing. This isn't proof. It's a scenario, but one rooted in the only life we know. If life started in such a place, methane might be its first language, echoes of early Earth, cut to an artist's rendering of the Archean Earth. 3.5 billion years ago, green oceans, hazy orange sky, rich in methane. Our own planet once had a methane-rich atmosphere. Long before oxygen, methanogenic microbes ruled the seas. They built the greenhouse blanket that kept Earth warm under a faint sun. Only after photosynthesis evolved did oxygen rise and methane fall. Looking at K2-18b may be like looking back in time at our own world's youth, a glimpse of what a thriving biosphere looked like before oxygenation, a living planet in its microbial age, exhaling methane instead of oxygen. Narrator's voice lowers. Are we peering across light years only to see our own past staring back? The isotopic puzzle, visual. Mass spectrometer peaks comparing biological and geological methane. On Earth, biological methane is lighter. Its carbon atoms prefer certain isotopes. If we could measure the isotopic ratios on K2-18b, we could distinguish between life and geology with far more confidence. Webb can't yet do this, but next-generation instruments may. A single isotope pattern could be the smoking gun of alien metabolism. Until then, we watch the patterns over time. Do methane levels fluctuate seasonally? Do they spike and fade like plankton blooms? Each variation would tighten the case for life. A living atmosphere, opening scene, slow-motion clouds rolling over K2-18b's horizon, not white like Earth's, but tinted teal and rose by exotic chemistry. They drift in layered bands, glowing faintly under a dim red star. Narrator, quiet, inquisitive. We have followed methane up from the surface, watched it accumulate in the sky like an invisible tide. But methane may be only the beginning. Imagine an atmosphere not as empty air, but as an organ, layered, structured, alive. Could K2-18b's atmosphere itself be a living, breathing system? Tonight we step inside that sky and wander through its strata, each layer a potential habitat, each chemical trace a whisper of metabolism, a planet's air. With many stories, visual, animated cross-section of K2-18b's atmosphere showing distinct bands, lower haze, mid-level clouds, upper thin gas. On Earth, our air is a transparent stage where weather plays out, but it's also an ecosystem. Microbes hitch rides on dust at high altitudes. Spores drift between continents. Tiny plankton pump oxygen into the sea and carbon dioxide into the air, shaping climate over eons. K2-18b magnifies that idea. Its gravity holds a deep, hydrogen-rich envelope tens of times thicker than Earth's. Pressure and temperature shift dramatically with altitude. Each level offers its own chemistry, light, and energy. To an alien microbe, this sky could be an ocean turned upside down, layers stacked vertically instead of horizontally. Narrator leaning in. Could each layer host its own form of life, feeding the one above or below like trophic zones in a forest canopy? The chemistry ladder, visual, chemical symbols cascading down through colored layers. Webb's spectra hint at a stratified atmosphere. Lower levels show water vapor and methane. Higher levels show hints of dimethyl sulfide, carbon dioxide, and haze particles. These aren't just random SM. Self-regulation. The Gaia echo, visual, a slow pulse of gas fluxes moving up and down, like a heartbeat across the planet. On Earth, living systems regulate our climate. Plants draw down carbon dioxide, microbes recycle nitrogen, ocean plankton produce dimethyl sulfide to seed clouds. The combined effect keeps conditions within a narrow band suitable for life. A feedback loop we call the Gaia hypothesis. K2-18b's layered atmosphere might do the same. Methane levels too high? Mid-altitude microbes consume it, releasing other gases. Dimethyl sulfide seeds clouds that modulate the star's heat. Lower layers buffer temperature swings. Upper layers shield harmful radiation. Each stratum performing a role, not by design, but by coevolution. Narrator. It's a radical thought. An entire sky acting like a single organism, self-balancing through countless unseen metabolisms. Floating life forms. Visual. Artist's concept of balloon-like organisms drifting in a pastel sky, thin filaments trailing downward. If gravity and chemistry allow, K2-18b might harbor not only microbes but larger, free-floating life. On Earth, jellyfish drift in currents, and plankton form colonies kilometers wide. In Jupiter's imagined gas bags of science fiction, life floats in hydrogen skies. Picture translucent sacs filled with lighter gases, rising and sinking to find the right temperature. They absorb chemical nutrients from upwelling plumes, excrete others that seed new reactions. They are not anchored to any surface. For them, the atmosphere is both sea and soil. Such beings would leave layered signatures, not just methane but cascades of intermediate molecules, each a clue to an aerial food web, a planet-breathing visual, time-lapse of gas concentrations pulsing with K2-18b's seasons. Webb's instruments are still crude compared to the scale of a planet, but even now scientists search for lessons from Earth's high frontier, visual, micrographs of microbes captured from Earth's stratosphere, then a view of volcanic plumes injecting particles skyward. In 2018, scientists captured living bacteria 12 kilometers above Earth's surface. Spores have been found even higher. Storms loft dust and microbes into the stratosphere, where they survive in cold and UV light. Earth's upper air is not barren. It's a thin extension of the biosphere. Now scale that up. Give the atmosphere more depth, more chemical energy, and a constant supply of nutrients from below. You have not just a few drifting microbes, but whole aerial ecosystems. K2-18b may be what our own high atmosphere could become if it were thick enough to support sustained life. Metabolisms we haven't imagined, visual. Abstract art of alien chemical cycles, glowing loops of elements we don't use on Earth. We should also be humble. Life elsewhere may not follow Earth's menu. Hydrogen and methane could be fuels or waste products. Sulfur chains might replace oxygen. Exotic catalysts could drive reactions we've never seen. Our instruments translate spectra into Earth-based molecules because that's what we know. But a truly alien metabolism might appear as mysterious haze or unexplained absorption feature. In K2-18b's layered sky, we may already be seeing the fingerprints of life we don't yet recognize. Narrator, what if our notion of biosignatures is like a 15th century sailor trying to spot a radio signal? We might be looking right at a living system and calling it a cloud. The air as archive, visual, particles and droplets drifting upward, carrying chemical stories from the surface. An atmosphere also records its world below. Every volcanic outburst, every metabolic surge, every seasonal cycle is etched in its composition. On Earth, ice cores preserve these changes for hundreds of thousands of years. On K2-18b, the air itself may be a living archive, continually refreshed, continually expressing the sum of the planet's processes. Reading that archive requires patience and multiple passes. Each observation Webb makes is a single snapshot of a vast, dynamic symphony. What comes next? Visual. Montage of planned missions. Ground-based ELTs, future space telescopes with coronagraphs. Scientists dream of instruments that can peel apart an atmosphere layer by layer, measure isotopic ratios, even map clouds. Within our lifetimes, we may move from hints to detailed portraits, from the first suggestion of life to an atlas of alien metabolisms. When that day comes, K2-18b may be remembered as the first place we glimpsed a living atmosphere, a whole world whose air was its biosphere. Narrator: for now we stand at the threshold, watching colored traces on a screen, trying to imagine the beings or systems that might lie behind them. Birthplaces of worlds, opening image, a vast dark nebula shot through with threads of starlight. At the center, a young star glows like an ember. Around it, 3 concentric bands of shimmering material arc like Saturn's rings, but hundreds of millions of kilometers wide. Narrator: calm, inviting. In the last chapter, we drifted through a living atmosphere, a sky that might be more organism than air. Now we travel even farther back in time, not to a world already alive, but to the places where worlds are born. Tonight, we enter the nursery of Antel, a young star hidden in a dusty arm of our galaxy. Here, 3 colossal rings of dust, ice, and organics circle like a cosmic carousel. They are not mere decoration. They are the raw ingredients of new planets, the echo of our own solar system's beginnings. The star at the center, visual. Slow zoom toward a young, orange-tinted star flickering through gas. Antel is a star still in its adolescence, hot, restless, shedding jets of gas from its poles. Around it swirls a protoplanetary disk, a flattened cloud left over from its birth. Over time, such disks coalesce into planets, moons, and comets. But Antel's disk is extraordinary. 3 distinct, widely spaced rings separated by dark gaps, as though unseen hands have sculpted it. Astronomers call it a 3-ring circus. It's more than a poetic phrase. It hints at hidden actors shaping the stage. Ring 1, dust and pebbles, visual, close-up of tiny grains glinting in starlight. The innermost ring hugs the star where heat vaporizes ice. Here the material is mostly silicate dust, tiny rock fragments only microns across. Colliding and sticking, they form pebbles, then boulders. Each collision is a coin toss between destruction and growth, yet over millions of years, islands of solid matter emerge. These are the seeds of rocky worlds, the analogs of Mercury, Venus, and Earth. When you see the golden glow of Antel's inner ring, you're looking at trillions of potential planets in their earliest form, grains no bigger than smoke, waiting to become continents. Narrator reflective: was our own planet once just a handful of such dust, orbiting unnoticed around a young sun? Ring 2, ice giants in the making visual. Shift to the cooler, bluish second ring where ice crystals sparkle. Beyond the star's heat lies the frost line. Here, water vapor freezes into ice, coating dust grains like frosting on seeds. Ice is sticky. It speeds up growth. In this band, cores of future gas and ice giants may already be forming, sweeping up debris and carving gaps. The dark spaces between Antel's rings may be the footprints of such nascent worlds, their gravity vacuuming paths through the disk. The second ring glows faintly blue in infrared images, a sign of its frozen bounty. In a few million years, this region could host titans like Neptune or exotic hybrids unlike anything in our solar system. Narrator: we are watching planets carve themselves out of chaos, sculptors invisible except for the empty lanes they leave behind. Ring 3, the organic reservoir, visual. A cold, reddish outer ring, rich with complex molecules. The third and farthest ring is the most mysterious. Here, sunlight is weak, temperatures are near absolute zero, and chemistry slows. B. Narrator: was it such a ring that seeded our young Earth with oceans and chemistry? Are we watching, in real time, the prelude to alien biospheres, the hidden sculptors, visual, artist's concept of unseen protoplanets creating waves and spirals in the disk? The crisp gaps between rings aren't empty by accident. When a growing planet reaches a certain mass, it can push material aside, creating a trench in the disk. Each gap at Antel may be a signature of a planet in formation, a ghostly silhouette revealed only by the void it leaves. Like a crime scene investigator tracing footprints in dust, astronomers use these gaps to infer the masses and orbits of hidden worlds. In this way, we may already know the layout of CENTEL's future solar system before its planets are born. Echoes of our origins, visual, dissolve from CENTEL's disk to an artist's reconstruction of the early solar system. Our own sun once wore such a disk. Out of its rings came the familiar lineup of worlds, from scorched Mercury to icy Pluto. Meteorites still carry isotopic memories of that time. By studying CENTEL, we're looking into a mirror of our own past, a chance to see how common or rare our pathway was. Did life's prerequisites begin in such rings everywhere, or was our solar system's chemistry a cosmic fluke? CENTEL's triple ring offers data we've never had before, a living laboratory of planetary genesis, from chaos to order, visual. Time-lapse simulation of dust clumping into planets, planets migrating inward and outward. Protoplanetary disks are dynamic. As planets grow, they can drift, swapping places, scattering smaller bodies like cosmic billiards. Some worlds may be flung into interstellar space, others spiral inward and perish in their star's fire. Yet out of this turmoil comes order, stable orbits, mature planets, and sometimes the conditions for life. Webb's technological triumph, opening image, a view of the James Webb Space Telescope floating in the darkness, its golden hexagonal mirror panels gleaming faintly. Around it, a blaze of starlight. Superimposed lines of code and faint signals drift like ghostly script. Narrator, calm, almost a whisper. We've soared across alien skies and peered into the birthplaces of worlds. Yet none of those visions came to us directly. They were teased from the edge of nothingness by a single machine, floating 1,000,000 miles from home. How does one telescope pluck a whisper of a faint planet from the thunderstorm of its star? Tonight we step behind the curtain, into the technology of Webb itself, a star's roar, a planet's whisper, visual, an animation of a bright star overwhelming the faint glow of a nearby planet. A star outshines its planets by millions, sometimes billions of times. Imagine trying to hear a lone flute in the middle of a hurricane. This is the challenge astronomers face. Light from the host star floods every pixel, drowning the feeble reflection of an orbiting world. Yet Webb listens. It hears the flute, its tools, coronagraphs, infrared detectors, and algorithms act like cupped hands around an ear, shielding and amplifying the signal until the melody emerges. Narrator leaning in. How does this work? What's the magic behind the golden mirror? The coronagraph's eclipse. Visual. The outline of a small dark disk sliding in front of a bright star. The first trick is an artificial eclipse. Webb's instruments carry coronagraphs, devices that block a star's light inside the telescope itself. They are like tiny, precisely shaped masks, inserted into the beam to dim the stellar glare while letting the surrounding light through. With the star's roar muffled, the faint glow of a planet becomes detectable. Patterns once lost in the blaze start to emerge. Seeing in the dark, infrared vision, visual. Colors fade to black, then reappear as glowing infrared maps. Webb doesn't look at planets in visible light. It sees in infrared the glow of heat. At these wavelengths, the contrast between a star and its planets is less brutal. Warm worlds emit their own faint thermal light. Cool atmospheres imprint subtle patterns. To catch this glow, Webb's detectors are cooled to just a few degrees above absolute zero. Each pixel is a supersensitive ear listening for single photons. Without such chilling, the telescope's own heat would drown the signal. Narrator. We built a machine so cold it can feel the warmth of a planet 120 light-years away. A mirror of many eyes, visual, the 18 hexagonal mirror segments aligning, golden and delicate. Infrared light demands large collecting area. Webb's primary mirror spans 6.5 meters, too big for any rocket fairing. Engineers solved this by splitting it into 18 hexagons that folded up for launch, and then unfolded in space like a golden origami flower. Each segment moves on microscopic actuators, aligning with nanometer precision until they act as one flawless surface. This mirror doesn't just reflect light, it sculpts time. Every photon bouncing off it began its journey before human civilization existed, and yet now, guided by gold and gravity. It converges on a single point. Algorithms as astronomers, visual. Streams of data pouring from the telescope into a supercomputer, turning into graphs and images. Even with coronagraphs and infrared detectors, what arrives on Earth is not a photograph. It's a torrent of numbers. Fluctuations in brightness at different wavelengths, faint dips that may last only minutes. Advanced algorithms sift this data, correcting distortions, subtracting noise, hunting for periodicities. They model the star's behavior, account for the telescope's quirks, and the symphony of calibration, visual, engineers in clean suits adjusting a test mirror, graphs stabilizing. None of this happens automatically. Before Webb could glimpse a single exoplanet, teams on Earth spent months calibrating every sensor, every mirror segment, every mask. They used distant stars as tuning forks, aligning the optics until images snapped into focus. They mapped stray light, measured detector quirks, and fed the corrections into software so that science could begin. This symphony of calibration is invisible to the public, but without it, Webb would be blind. It is the slow, patient work behind every headline about a new discovery, pulling planets out of starlight visual, overlapping spectra showing a faint dip where methane absorbs. The result of all this effort is astonishing. A faint dip here, a subtle notch there, and suddenly you're reading the chemistry of an atmosphere you will never touch. Methane, water vapor, dimethyl sulfide. Each appears as a tiny subtraction in a rainbow. With enough observations, you can reconstruct temperature, pressure, even cloud layers. We are not just detecting planets. We're performing remote sensing on worlds light years away, using instruments more delicate than any that have ever flown. The edge of what's possible, visual. Webb drifting against the backdrop of the Milky Way, its sun shield glowing faintly. Webb operates at the edge of physics. Mirrors aligned to tens of nanometers. Detectors counting individual photons. Algorithms pushing statistical limits. Every spectrum you see is a triumph, not just of engineering, but of cooperation. Thousands of people across continents, building a single eye for humanity. Narrator. It's easy to marvel at alien worlds. It's harder to remember the world that built the tool to see them. Closing teaser visual. The camera pans from Webb to a montage of future telescope. The next great survey, opening image, a star field thick with glittering points of light. As the camera drifts forward, subtle circles and labels appear around dozens of stars, like an invisible network revealing itself. Narrator. Low, reflective. For centuries we mapped coastlines. Then we mapped planets. Now we're mapping life itself, or at least the conditions where life might bloom. In the quiet hum of observatories and the silent watch of space telescopes, a new campaign is beginning. It is not a single mission but a coordinated hunt, a census of the invisible. What if within a few decades we could catalog living worlds the way we catalog galaxies? What if the night sky itself is full of signatures waiting to be read? From scattered discoveries to a census visual, archival images of early exoplanet discoveries, tiny dots, faint dips on graphs. The first exoplanets were like messages in bottles. We found them one by one, each a shock, each a headline. Hot Jupiters, super Earths, mini Neptunes. Scattered finds across the galaxy. But random discovery is no longer enough. To answer the oldest question, are we alone? We need a systematic survey. Astronomers call it the Coming Biosignature Census, a program to measure the atmospheres of hundreds of nearby worlds, searching for chemical fingerprints of life. Not speculation, not wishful thinking. Data, gathered the same way we measure weather on Earth, but at interstellar distances. Narrator. It's a leap from exploration to inventory, from glimpses to patterns. The tools of the new era, visual, Webb handing the baton to future telescopes, LUVOIR, Habex, Life, ground-based giants. The James Webb Space Telescope cracked the door open, proving that even thin traces of water and methane can be detected across light years. But the next generation will push further. Giant segmented mirrors, starshade. On the ground, telescopes like the extremely large telescope in Chile will use adaptive optics to cancel Earth's own atmospheric blur, while arrays of radio dishes tune their ears to the faintest transmissions. Narrator, musing. We are building a planetary MRI for the cosmos. But even the best hardware is only half the story. Eyes on the sky, visual. A flow of raw data turning into recognizable planetary signatures under an AI's gaze. Each observation produces terabytes of information, dips in brightness, shifts in color, spectral lines. Hidden inside are patterns too subtle, too complex for human eyes alone. This is where artificial intelligence enters, not as a novelty, but as a necessity. Neural networks trained on millions of simulated planets can spot the telltale signs of life-supporting chemistry, oxygen paired with methane, unusual seasonal variations, out-of-equilibrium atmospheres. Algorithms compare hundreds of worlds at once, finding correlations no human analyst could notice. In a sense, AI becomes our extended perception, a pattern recognition organ grafted onto civilization itself. It's as if the planet Earth is growing new senses, able to detect life on distant shores. Narrator whispering, when the first unmistakable biosignature appears, an AI may be the first to see it. Beyond biosignatures, the technosignature frontier, visual, faint, unnatural pulses on a radio spectrum, a geometric glint crossing a star. But biology may not be the only story. Alongside biosignatures, a parallel search is rising, the hunt for technosignatures. Not just life, but technology. Waste heat, unusual atmospheric pollutants, laser pulses, coordinated radio bursts, even the glint of artificial structures transiting a star. These are not science fiction props, but measurable phenomena. Our own planet, seen from light years away, would show oxygen from life. The Neighborhood Watch. 200 star systems, visual. A three-dimensional map of the solar neighborhood. Points of light glow as the camera sweeps through. For the first time in history, astronomers have a manageable sample. About 200 nearby star systems within roughly 100 light-years, many with known planets. This is our cosmic neighborhood. We can visit it with light alone, returning year after year to watch seasons change, atmospheres shift, perhaps even continents drift. The plan is audacious but clear. Survey every potentially habitable planet in this volume, build a database of their atmospheres, look for anomalies, track them over time. Not a snapshot, but a movie of living worlds. Narrator inviting. Imagine opening a catalog in 2050 and scrolling through real alien weather reports. Clouds over an ocean on Tau Ceti E, volcanic haze on a super-Earth, a faint chlorophyll edge on a world around Proxima Centauri. The next great survey is not a dream. It is a blueprint, patterns in the dark visual, rows of spectral graphs aligning into a grid like a DNA sequence. With hundreds of spectra, patterns emerge. Do most habitable planets have thick clouds? Do they cluster in certain orbital distances? Are oxygen-rich worlds rare or common? Do seasonal changes hint at vegetation, plankton blooms, or something stranger? By comparing many worlds, we can learn the rules of life's appearance even before we meet it. It's the difference between a single fossil and an entire field site. One tells you a creature existed. Many tell you how it lived, how it evolved, how it spread. Narrator. In those patterns may lie the first universal laws of biology. The human question, visual. Scientists at screens. Children in a planetarium looking up at a map of living worlds. Yet behind every spectrum is a human story. Teams of engineers, programmers, and observers will spend their careers on a single target, a single hint of a chemical line. Students entering university today may be the ones who confirm the first life-bearing exoplanet by the time they retire. And when that happens, how will it change us? Will it humble us, inspire us, frighten us? The survey is not only a scientific project, it is a mirror held up to humanity, showing what we choose to look for and how patiently we search. Narrator thoughtful. We are about to map possibility itself. And maps have a way of changing the travelers. Closing teaser visual. The starfield fades. A lone pale dot glows in the darkness. The next great survey will not end with a single discovery. It will give us context, statistics, perhaps even a glimpse of the extraordinary hidden in the ordinary. Somewhere in those 200 star systems may be the first confirmed living world beyond our own, or perhaps dozens. But what happens after the census, after we know where life dwells? In our next chapter, we'll explore the step beyond detection, how we might reach out across that gulf, communicate, or even one day visit the end of cosmic loneliness. Opening image: a night sky stretching from horizon to horizon. Millions of stars glimmer like grains of salt scattered across black velvet. Slowly the view tilts until Earth itself appears, a blue-white marble suspended in an ocean of dark. Narrator: calm, resonant. For all of human history, the stars have been silent. We gazed up, wondered, built stories and religions and science out of their light, but never heard an echo. Earth seemed like an island, luminous and alone. Yet somewhere between a telescope's mirrors and an astronomer's code, that silence began to fracture. 99.7%. That is not a whisper of possibility. It is a drumbeat of certainty. It is the percentage flashing on the monitors of the James Webb team after months of verification. It means the light crossing empty space for more than a century carried a truth. We are not the only living world. The moment of realization. Visual. Scientists in a control room holding their breath as a spectral line brightens on a graph. Numbers can seem cold, but sometimes they break the world open. On that day, the numbers did exactly that. Layers of atmosphere on K2118b showed methane, dimethyl sulfide, patterns no geologist or meteor could conjure without life. Cross-checks, simulations, and alternative models fell away one by one. It was as if a door in the sky had cracked, and through it, a second garden whispered back at us. Narrator, softly. How do you describe the instant when humanity's oldest question, are we alone, shifts from mystery to memory? Science caught up with wonder, visual. Ancient cave paintings of stars dissolve into satellite imagery of the Milky Way. The answer did not descend as revelation. It was built by people, by engineers who polished mirrors until they sang, by coders who wrestled noise out of spectra, by mission planners who aimed a telescope with the precision of a surgeon. Step by step, hypothesis by hypothesis, science did what myth always promised. It found company in the void. And yet the moment was not only technical. Around the world, headlines burst, classrooms paused, elders wept. For the first time, the sentence, "We are not alone," was not speculation, but observation. Narrator, wondering, what does it do to a species to wake up from cosmic solitude? Shifting philosophies. Visual. Statues of philosophers. Telescopes turning. A child holding a smartphone up to the night sky. Every era has a Copernican shock, a revelation that redraws our map of existence. First, Earth was not the center of the cosmos. Then, the sun was just another star. Now, life is not an Earth-only experiment. Each shift humbled and enlarged us at once. Some philosophers say loneliness was the last frontier of anthropocentrism, the comforting belief that even if we were small, at least we were unique. That frontier just collapsed, and with it, our definitions of alien, neighbor, and perhaps even home. Narrator, inviting. Does life on K2118b pray, sing, build, dream? Or is it microbial, an ocean of cells unaware of the stars above? In either case, the universe feels different. We are no longer the story. We are a chapter. The mirror effect. Visual. The planet's reflected light superimposed over a human eye. Oddly, finding another living world forces us to see ourselves more clearly. Our atmosphere, our biodiversity, our own fragile equilibrium appear not as background, but as a signature, a signal someone else could detect. We have become our own exoplanet. In classrooms, children now compare Earth's spectral fingerprint to K2-on-8b's, the way past generations compared flags or maps. The sky is no longer out there. It is a neighborhood, and we are both residents and observers, narrator, reflective. Perhaps the greatest lesson of the 99.7% is not about them, but about us. Science accelerates, questions multiply, visual, proposals for new telescopes, robotic probes, and daring starshot sails filling a conference wall. Certainty does not end inquiry, it multiplies it. If one living world exists, how many more? Are there patterns, chemical, orbital, evolutionary, that predict life? What factors tip a planet from sterile to fertile? Already, the biosignature census is expanding. Budgets once seen as extravagant now seem inevitable. New missions are designed not just to detect life, but to characterize it. Ocean depth, seasonal change, even the color of alien vegetation. Narrator, with a hint of awe. We thought the question was, is anyone out there? Now the question is, who are they? And how far does life's web extend? The emotional horizon. Visual. People watching the sky from cities, mountains, deserts, messages trending online. For individuals, the revelation is subtler, but no less profound. Poets find new metaphors. Faiths reinterpret scriptures. Science fiction writers scramble to catch up with reality. Some feel wonder, others dread. If life is common, so might be struggle, competition, extinction. The cosmos grows both friendlier and more complex. Yet there is a quiet hope threaded through the uncertainty, the sense of a shared belonging that stretches beyond species and planets. Loneliness, even the cosmic kind, has always been a human ache. Now it may be easing. Narrator. The night sky does not feel empty anymore. It feels alive. From certainty to contact, visual, an artist's rendering of a laser sail unfurling in starlight. A faint radio pulse across a graph. Certainty invites the next leap. If we know where life dwells, do we dare to speak? Should we send our own signal? Mathematical, chemical, or even a probe that might skim another world's atmosphere within a human lifetime? Or do we listen longer, trying first to understand? Entire new disciplines are forming. Exoethics, interstellar anthropology, cosmic diplomacy. The questions are as old as the Drake equation, but suddenly tangible. The horizon of our future may include not only detection, but dialogue. Narrator, curious. How does a species prepare for a conversation across centuries of light? Humanity's place in a living universe. Visual. Earth rising over the moon fades into K2-on-8b rising over its own ocean. In discovering another living world, we are discovering the scale of life itself, an ancient, distributed phenomenon that may have begun soon after the first stars formed. Perhaps the cosmos is not a museum of dead rocks, but an archipelago of evolving islands, each with its own story. This does not make us insignificant. It makes us participants. We are no longer the lonely observers of a silent stage, but actors in a much larger play. Narrator, softly. We are not the only verse, but we may still be a rare and precious line. Closing reflection. Visual. The night sky returns. This time, subtle pulses of color link star to star, like a faint neural network. The end of cosmic loneliness is not an end at all. It is a beginning, a doorway to a universe that is older, richer, and stranger than we imagined. 99.7% is not just a number. It is a mirror cracking, a horizon expanding, a signal waiting. Somewhere right now, light from K208b's sky is still crossing space toward us. By the time it reaches our telescopes again, our understanding will have changed yet again. We will have built new instruments, new questions, new hopes. Narrator, whispering. The stars are no longer just distant fires. They are possible neighbors, and in their light, we may, at last, see ourselves. Teaser for what comes next. Visual. The faint silhouette of a sail-driven probe pushing outward, fading into darkness. In the next chapter of this journey, the question will shift once more. From discovering life to reaching it, from certainty to connection. How do we cross the gulf, not just with telescopes, but with touch, message, and meaning? The story of the first living world beyond Earth is only the prologue to the story of meeting it.